Hi, my name is Terry Brown. I'm a mechanical engineer and university lecturer, and in this video I'm going to go through the solution to this engineering mechanics problem. So let's start by reading through the question and understanding what it is that we're trying to solve. So if we read through the question here, we're told that we have a beam shown in the figure, so we can see that down here. So we have our beam supported by a pin at A and also supported by a strut with pin connections at C and D. And then we have some loading. We have a 4 kilonewton load applied here, and we also have a 4 kilonewton meter couple applied at NB. And then we're asked to determine the support reactions on the beam at A and C. So we want to know what the support reactions are at this support here at A and also at this support here at C. Okay, so let's consider our approach to the solution. So what we'll do first, as we do in most engineering mechanics problems, is to firstly draw a free body diagram of the object that we want to analyse. So in this case we're going to draw a free body diagram of the beam, ABC. Then we'll apply our equations of equilibrium that we'll use to solve for our unknowns. And of course our unknowns in this case are our reactions at the supports that we're asked to determine in the question. Okay, so let's start with drawing our free body diagram. So start off with the beam. So I've just copied over here our picture for reference, and I've drawn the free body diagram, or the start of the free body diagram, which is just the body that we're analysing, in this case the beam ABC, and I've removed everything that's connected to that beam. So usually my next step in solving the problem is to just add on the loads that are given. So we've got our applied force and our applied moment. So just draw those on, and we write also the values for those loads. So now we need to consider what's happening at our supports at A and C. So let's start with the support at A. If we go over to our picture, we can see here that we've got a pin support. So we know when we draw our forces here, we'll need a vertical reaction force and a horizontal reaction force that's provided by that support. So let's go ahead and draw those in. So we have our vertical reaction force and our horizontal reaction force. You can try and work out the sense of those forces. If you're not sure, you can just assume a direction. So I've just assumed upwards for the vertical force and to the right for the horizontal force. And you should know from previous work that if the answer comes out to be negative, then that tells you that the sense of these forces are opposite to what we've shown on the free body diagram. Okay, so on our free body diagram, having drawn the reaction forces, we should label those. So we'll go ahead and call this one RAY and the horizontal component RAX. Okay, so now we need to consider what's happening at the connection here at C. So here we've got a connection between the beam and this strut CD, and we're told that it's pin connected at both ends. So this component here is a two-force member in equilibrium. So having recognised that, that enables us to put on our unknown force here in its known direction, because it being a two-force member in equilibrium, we know that the force must be directed along the line joining the points C and D. So on our free body diagram, we'll just show that direction. So in this case, it's 45 degrees because we've got 1.5 meters here and then 1.5 meters here. So we know that this angle here is going to be 45 degrees. And then we can put in our force acting along that line of action. So that's our unknown reaction force from the support of the strut at point C. This time it's fairly easy to work out the sense of the force. So this force here is going to be pushing down the moment here is going to be tending to rotate this thing around clockwise, so this force here is needed to push it back up to keep it in equilibrium. If you can't do that thought experiment and work out the sense of this force, again, it doesn't matter whether you have it acting upwards to the right or downwards to the left. When you do your calculations later on, if you get a negative answer, then you just know that you've assumed the wrong sense for that force. Okay, so having drawn that force, let's give it a label. So we'll just call it R subscript C for reference. Okay, so we've now completed step 1 of our solution. We've drawn the free body diagram. Step 2 was to apply our equations of equilibrium. Now you can apply any of the 3 equations of equilibrium, some of the moments, some of the forces in the horizontal direction and some of the forces in the vertical direction equals 0. But as with most problems like this, usually the easiest one to start with is the sum of the moments, because that will generally enable you to end up with an equation where you have only one unknown. So we're going to take moments about point A in this case, because by doing that, the moment effect of RAX, of course, will be 0 because it passes through point A, and the moment effect of RAY is also 0 because it also passes through point A. So when we calculate the moments, the only unknown force that will be causing a moment about point A will be RC. So we need to define which sense of the moment is positive. So usually anti-clockwise we take as positive, so we've just indicated that on our formula here. And for equilibrium, sum of all of the moments about point A is equal to 0. So once we've done that, we can start looking at the forces and applied moments. So I'll start here with the applied 5 kilonewton meter couple. So that can just go straight into our equation here, and it's going clockwise. Okay, so we can see over here rotating clockwise, so therefore that's going to be a negative moment according to our sign convention. The next thing that we'll look at is our 4 kilonewton force here. So that's acting down here. Its perpendicular distance from point A is this total length here, 2 times 1.5, so 3. So that's what we've got down in our equation, 4 times 3. And we again need to check whether this is positive or negative moment. So this force here about point A will be tending to rotate this around clockwise about point A. Okay, so this force, if you imagine that it's pinned here at A, if we push down here with this 4 kilonewton force, then this beam is going to rotate clockwise. So that will be a negative moment. So we put that in our equation here. Then next we have our force RC from the strut. Need to work out the moment of that force. So we could work out the perpendicular distance, which would be perpendicular distance down here like this. Okay, so we could try and work out that length, D, and then say the moment of RC about point A is RC times D. Or we could find the components of RC like this, vertically and horizontally, and then just work out the moment effect of those components about point A. So we know that RC, or let's say, look at the horizontal component. The horizontal component is going to be passing through point A, so that's going to have a 0 moment, and our vertical component acts at perpendicular distance of 1.5. So probably the easiest thing to do is to find the components of RC in vertical and horizontal directions. So that's what we're going to do. Okay, so I've just removed all that blue writing just for clarity, and we've put in our horizontal and vertical components as we discussed, and we can also label those, or we put on the values in fact. So here the vertical component will be RC sine 45. So if you imagine your little right angle triangle, and here's our triangle here, and the length of this side of the triangle is the same as the length of that component, and this is our angle here, 45 degrees, so this is the opposite side, so therefore the length of this side will be RC sine 45. So let's get rid of that, and our horizontal component likewise will be RC cos 45 degrees because that's the adjacent side to this angle. Okay, so let's now add into our equation the moment effect of this force. So it will be RC sine 45 times this perpendicular distance, which is 1.5. Is it positive or negative moment? So again, if we imagine that it's pinned here and we push up with this force, is the body going to rotate clockwise or anti-clockwise? I think you can easily imagine that if we push up here, it's going to rotate anti-clockwise. So this is a positive moment that we can then put in our equation down here. So there are all the moment effects, and all of that is equal to 0. So we now have one equation and only one unknown, which is our unknown force RC in our strut CD. So do the algebra, rearrange the equation and solve for that unknown force, and in this case we get 16.03 kilonewtons. Okay, so our next step is to use the next equation of equilibrium, and I'm going to use some of the forces in the vertical direction equal 0 and taking upwards as positive. So now we just need to work through each of our forces in turn. So we have RAY, which is at the moment unknown. We'll have the vertical component of RC, which we now know from our previous work we did here. So RC sine 45, again acting vertically upwards, so positive, and we have our 4 kilonewton force at the end here, which is in the negative direction, and all of that is equal to 0. And again, we can substitute RC into here, do the algebra, and solve for our unknown force RAY. And as we see here, that comes out to be negative, which indicates to us that what we drew up here, what we assumed as the sense of this force RAY, was incorrect. It's actually acting downwards. Okay, so now we can use our next equation of equilibrium. Some of the forces in the horizontal direction equal 0, indicating to the right as positive. And again, do the same thing. So we have RAX up here, so that's in our equation, acting to the right, which is positive. And then we have the horizontal component of the force RC, so RC cos 45, and we have no other horizontal forces acting, so that's all equal to 0. So we can rearrange the equation and solve for our unknown RAX by again substituting in for RC that we found earlier. And again, we see that we've got a negative number here, which indicates that what we assumed up here was incorrect for the sense of RAX. And we can see that that will be the case, because if we have RC correct here, then this horizontal component is to the right. Therefore, for equilibrium, this horizontal component has to be to the left. Okay, so as I've said in previous tutorial videos, never go back and change your free body diagram. Just leave it as it is, and the negative sign will indicate that that this force is actually acting to the left. Okay, so once we finish that, we now need to round up our answers to an appropriate number of significant figures and summarise our findings. So our final answers, RC will be 16.0 kilonewtons. So typically round to 3 significant figures, because that's about the best we can get with most input data. Not in that's so sometimes you can get better than 3 significant figures, but as a general rule, if you're not taking extra effort to make sure that your input values are known to better than 3 significant figures, then always round up to about 3 significant or round up to 3 significant figures. Okay, so then we have RAX is RAX here is 11.3 kilonewtons in the negative direction, or in the opposite direction to what we've shown on our free body diagram. Okay, so usually I'll just indicate that next to my answer. And then finally RAY equals minus 7.33 kilonewtons, and again I'll just indicate that the sense of that force is actually in the opposite sense to what's shown on the free body diagram. Okay, so that's the end of the problem, apart from going back and checking all of your answers, which of course you always should do. And I hope this was helpful to you, and I'll see you in the next video.